Welcome to this ECO webinar. So I present you Yannick Sarrazin, who will attend this webinar for 1 hour and a half, something like that. Thank you, Yannick. Go ahead.
Okay, thank you, Nathalie, for this introduction. So my name is Yannick Sarrazin. I'm working at Cea Main, south of France, close to ITER site. I'm going to speak about HPC modeling, HPC meaning high performance computing, modeling of turbulent transport in tokamak plasmas. And I will highlight a few recent results that we got in this area regarding critical physical issues and of importance for ITER. So I have to acknowledge many of my colleagues and collaborators who are listed below, and this work was also performed within the framework of various European projects. ECO is one of them. TRACE and GENC provide us the computing facilities, and Eurofusion is also for fusion some support for physical projects. So the outline is the following. I will briefly review some basics regarding magnetic configuration and confinement in tokamak plasmas, mainly focusing on the issue regarding transport and mostly on turbulent transport, because you will see that it's the dominant contributor to the transport in tokamak plasmas. Then I will detail a little bit more what is this turbulent transport and what are the issues regarding modeling. And I will focus on the core transport, where the plasma is the hottest and which requires a kinetic approach. As we will see, there is a broad range of time and spatial scales which require HPC. And then the last 2 points will deal with the necessity to take into account non-local interactions, and especially the interaction between electron scales and ion scales on the one hand, and on the other hand, between ion scales and equilibrium scales. And as we will see, those interplays between various scales are mediated by flows, by large-scale flows. Finally, I will conclude by mentioning some effort which is developed right now, which we can see at the new Everest, which is the development of gyrokinetic core towards the core edge interplay. So let's start. So fusion aims at producing fusion power, and to have an estimate of the performance of the machine, we use the fusion gain, which is the ratio of the fusion power divided by the power injected to heat the plasma. And the target in ITER is to reach in steady state Q equal to 5, and for more performant dischargers Q equals 10. So the idea of fusion is to use, on Earth at least, is to use isotopes of hydrogen, so deuterium and tritium, which fuse to give an alpha particle, helium particle, plus a neutron. The neutron is not charged, so it's not confined by the magnetic configuration, and by impacting lithium, it will generate tritium, and then this tritium will be re-injected into the discharge to be part of the fuel. Also, the energy of the neutron, which is 4/5 of the total kinetic energy, will serve as energy production. Then the alpha particle is much more energetic than the deuterium tritium plasma, and before leaving the discharge, it will thermalize on the main ions and heat the plasma, so that the temperature remains at the right level for the fusion reaction to take place. So if you wish to obtain Q equals infinity, which is an ideal kind of tokamak plasma, then you reach what is called the self-heated plasma, where you no longer have to inject power to heat the plasma, and the alpha particles are sufficient to ignite the plasma and to reach the critical temperature. And to reach this, then you have to balance the losses, the thermal and radiative losses, by the heating of the alpha particles. And this condition of balancing losses and heating can be formulated in this criterion due to Lawson in 55, where you have a triple product: the density of the ions times the temperature of the ions times the energy confinement time has to be larger than a certain value. And here, the energy confinement time is the energy contained divided by the lost power. And what is important is that if you plot the amplification factor, the Q that we just discussed, versus this energy confinement time normalized to a certain value, then you can see that the amplification factor increases non-linearly with this tau E, energy confinement time, and diverges when tau E reaches the Lawson time, and the Lawson time corresponds actually to the ignition, where you do no longer need injected power. So to reach the ignition, then you need to have an energy confinement time of the order of a few seconds. In a tokamak plasma, the temperature is more or less prescribed, because the deuterium-tritium reaction is a threshold reaction, so you need to have a temperature of the order of 20 keV, and density, because this is the control confinement, the kinetic energy has to be smaller than the magnetic energy, and this leads to a density which is less than a certain value, and in the end you end up with a density which is of the order of 10 to the 20 per cubic meter. So the pressure, because the temperature is large but density is low, the pressure is just a few atmospheres, so not a large pressure. And most of the research regarding the improvement of the performance of fusion dischargers is to try to increase this energy confinement time. So how to confine this plasma at this very high temperature? So it's provided by a magnetic configuration with nested magnetic flux surfaces, which are nested tori. Here you have an example with the magnetic field lines, which are helical onto those surfaces, with the particles making cyclotron motion along those magnetic field lines. And at equilibrium, we will come back on the side, there are three motion invariants. These motion invariants are associated to the symmetries of the problem, and the symmetries are provided by, first, the two periodic angles, the two angles or periodic directions of the torus, the toroidal angle across the symmetry axis, the colloidal angle across the magnetic axis, and then there's another angle which corresponds to the cyclotron motion of the particle. So let's come a little bit more in detail on this issue of free motion invariant. Motion invariant meant that when the particle moves, it conserves a certain number of quantities, and the first one is the energy. The energy, the total energy of the particle, the kinetic energy plus the potential energy, is constant along the trajectory of the particle, provided the potential vector and the electric potential, and the vector potential do not depend on time explicitly. Then, in this case, only the total energy is conserved. The magnetic moment, which is the ratio of the transverse energy divided by the magnitude of the magnetic field, is what is called an adiabatic invariant. It's an invariant provided that the magnetic field evolves slowly with respect to the cyclotron motion which is the case actually in tokamak plasmas. And the third invariance is due to the axisymmetry of the problem, which is the fact that the system does not depend on the toroidal angle, and then you can show that the toroidal kinetic momentum P5 is a motion invariant as well. Notice, by the way, that P5 is the sum of two terms, and one of them is up to the charge of the particle is a level of the flux surface, meaning that when a particle moves, it moves at constant magnetic surface up to a small term, which is provided by the second component of the kinetic toroidal momentum. So obviously those invariants are conserved provided the symmetry are fulfilled, but there are some perturbations in the system that lead to a break of these symmetries, and turbulence are one of those possibilities. So turbulence is such that the energy is no longer conserved, because then the electric potential and the vector potential depend on time. And also the axisymmetry is broken because it develops small scales or scales perturbation along the toroidal angle. So particles are confined at equilibrium, but because of turbulence, they get unconfined. And this is the reason why there is some transport across the magnetic surfaces due to turbulence. We will come back on this issue in a minute. So just a little bit more regarding this magnetic configuration. So it's governed by a toroidal plasma current, toroidal current which is carried by the plasma, this magnetic configuration. And as you probably know, the whole magnetic configuration can become MHT unstable and lead to transient relaxation disruptions, which are the worst case, where the whole confinement is completely lost in a few hundreds of microseconds or a few milliseconds. But to avoid this kind of problem, then there's a kind of operational diagram which allows you to go across those instabilities. So turbulence, as I said, leads to a break of this invariance. Binary collisions also provide a way to transport heat and particle across the magnetic surface, because they break especially the adiabatic invariant, the collisions. And if we look at the turbulence which develops, the main properties of this turbulence are the following. It is balloon in the sense that it mostly develops in the low field side region, where the magnetic field is the smallest, because this region is unstable, while the high field side region is stable. It's basically small scale in the sense that it develops at a few iron Larmor radii, which is of the order of 1 centimeter, and the magnitude is not large, it's less than 1%, even 0.1% in the core. It can reach fairly large magnitude at the edge. So what are the main players in this turbulence? It comes from linear instabilities, and the main instabilities developing at the ion scale are the ion temperature gradient, so-called ITG, and trapped electron modes. Those are carried at, indicated by their name, either by the ions or by the electrons, but both of them share the same kind of features which I just talked previously. They are at the ion scale and they are balloon. They are actually analogous to the Rayleigh-Bénard instability in fluid. The order of magnitude of the growth rate is written here, so it's scaled like the square root of the diamagnetic frequency times the curvature frequency. So just retain, because it's not detailed here, that the main drive of the instability are the pressure gradient and the curvature of the magnetic field. And the curvature of the magnetic field plays the role analogous to an effective gravity in the Rayleigh-Bénard instability in fluid. The frequencies of the order of the diamagnetic frequency, either the ion diamagnetic frequency or the electron for the TEM. And by studying the linear analysis of the system, then we can draw a kind of diagram of where those instability take place. Not going too much into the details, there are a lot of references there. But what you can see on this diagram are 2 points mainly. This diagram tells you where the TEM and ITG instability are unstable. What you can see is that the TEM can become unstable by increasing either the density gradient, R over Ln, or the temperature gradient, R over Lt. R is the major radius, Lt is the gradient length of the temperature gradient. And the ITG, conversely, is only driven and stable by the temperature gradient, and conversely, the density gradient is stabilizing for ITG. So, density gradient and temperature gradient are the main drive for those instability. There are some other parameters which play an important role also. By controlling the threshold of those instability, one can mention the ratio of the ion over the electron temperature, the collisionality, which stabilizes the trapped electron modes, and the magnetic geometry as well. So once we know that the most of the transport, and so the energy confinement time, is governed by turbulence in Tokamak plasma, what are the main issues? Well, as you can see on this diagram here, plotting the energy confinement time experimentally measured in various machines as a function of a scaling law, which is a way to set that those measurements of the energy confinement time get a line on the same line with the smallest dispersion. And by getting the smallest dispersion, then you obtain the scaling law. And what you can see is that first three things. The first one is that the dispersion of the various points you can see on many machines is of the order of roughly 15–16%. So it's not negligible. The second point is that the scaling law of the energy confinement time depends mostly on one parameter, which is called rho star, which is the ratio of the ion Larmor radius, ρ, divided by the Tokamak minor radius, A. Rho star is fairly small, and it's even smaller when you go to ITER. And there's basically a factor of 2 with respect to the largest machine that we can run presently, which are JET and JT60 in Japan. And so the third point is that you can see that if you want to know what will be the energy confinement time in ITER, and consequently what kind of gain factor, capital Q, you can expect in ITER, then you have to make an extrapolation, assuming that the physics will be the same and that the discrepancy of the point is not too large so that you can be confident in the extrapolation. So actually ITER was designed on this scaling laws, and this is the reason why you need to have a large machine to increase the energy confinement time, because by constructing a large machine like ITER, then the minor radius is large, and then you reduce rho star. By reducing rho star, you increase a lot the energy confinement time. You need modeling, not only relying on those experimental scaling laws, because there might be new physics in ITER. So far, we do not expect strong discrepancy with respect to present machines, but you have to realize that in ITER there will be a fairly new physics in the sense that 2/3 of the heating of the plasma will be provided by the alpha particles So there will be self-heating. We will reach a regime in which the plasma will be burning. This will be a burning plasma, and then you will have energetic particles, the alpha particles, and self-organized heating. This is potentially a new physics. So how to address this issue of turbulent transport modeling in ITER and present-day machines? Actually, given the complexity of the task, it's made in two separate ways. First, the edge plasma for the minor radius normalized to the minor radius of the machine larger than typically 0.8, 0.9. Then the plasma is fairly cool, so that the mean free path is small, and because of that, and because of the complex geometry of the need to take into account the plasma wall interaction, the interaction with the neutrals, actually the modeling is made in using the fluid description, which is three-dimensional, so you rely on the equations regarding density, mean velocity, temperature, and so on. However, keep in mind that kinetic effects are important. So the sheath, parallel boundary, the ion orbit losses might matter and do matter, we know this. So there is some issue regarding fluid modeling in the edge. But so far, this is the best we can do. Regarding core turbulence, it's almost collisionless in core plasma. The reason being that the mean free path is extremely large, is of the order of a few kilometers, so 100 times the machine scale, and so kinetic description is mandatory. Kinetic description is using the Vlasov equation, but although it's almost collisionless, it's not completely collisionless, and you have to account for collisions. So they are critical collisions in the sense that they ensure the H theorem, so they ensure that the distribution function will relax toward the Maxwellian on long time scale, on collisional time scale. And also collisions are extremely important because they govern the flow damping. Another point also regarding collision is that impurity transport, impurities are all the species different from the fuel, deuterium and tritium. So these are alpha particles and also impurities coming from the interaction of the plasma with the wall. So impurity transport is also partly governed by collisions. So at least for those issues, collision should be accounted for. So I will focus now on the core turbulent transport before, in the end, coming back on the interaction with the edge. If you want to solve the core turbulent transport, then you have to take into account a broad range of time and spatial scales, which are presented here. Time is on the vertical axis, and spatial scales on the x-axis. So you go from the electron cyclotron radius, which is of the order of 10 to the minus 4 meter, up to the minor radius, a few meters. So you have 4 orders of magnitude in space, and in time you have basically 6 orders of magnitude. So covering all those scales at once is not affordable with present-day machines. So the idea is to separate the problem, and recent simulations have shown that actually we cannot completely separate the problem and perform the multi-scale approach. We need to take into account some interaction between various scales. The first one deals with the interaction between the ion scale and the electron scale turbulence. And this approach, as we will see, is performed within a framework which is called the gradient-driven turbulence, in the sense that within this approach, then we freeze the equilibrium scale. And the equilibrium scale will be prescribed, not evolving in time, and we will only look into the dynamics of the fluctuations at the ion and electron scales at this prescribed equilibrium gradient. The alternative approach, which deals with the interaction of the ion scale turbulence with the equilibrium scales, then has to account for the flux driven approach, in the sense that in this case you have to relax the fixed assumption of the gradient driven approach, and then let the equilibrium evolve freely by taking into account the back reaction of the turbulence of on the equilibrium scales. And in this picture, we will see that there are several mesoscale structures that develop, avalanches and zonal flow. I will come back on this later on. So obviously, the problem is fairly complex. If we start from Blasov, which is 6-dimensional, it's too numerically costly to be afforded by present-day supercomputers. So we can fortunately relax a little bit the constraints, and by noticing that the alarm or frequency is much larger than the typical turbulent frequency, by typically 3 orders of magnitude, and also by noticing the fact that the gyro radius is much smaller than the scale of the variation of the magnetic field, then we can replace the 6-dimensional modeling by a 5-dimensional modeling, which is called the gyrokinetic framework. And in this case, here you can see the transverse plane with the magnetic field transverse to the screen here, with a particle in red here having its cyclotron motion. And the idea of the gyrokinetic theory is to replace this particle by a ring of currents here, which can be polarized, but then you do no longer wonder where is the position of the particle in the circle. You just replace the particle position by a ring of current. And this is the idea or the spirit of the gyrokinetic framework. So the other properties of turbulence that you can use to reduce further the complexity of the numerical approach, you can use the fact that the turbulence is almost 2-dimensional, in the sense that, as you can see on this picture here of the turbulence simulation, you can see that the fluctuations are much elongated along the magnetic field lines, while they develop small scales in the transverse plane. The scales in the transverse plane, as I said previously, are of the order of the iron llama radius. Well, and I will not detail the other points, which are interesting, maybe too detailed at this level. So, since I mentioned that HPC needs are required, HPC is required, let's try to quantify a little bit more what are the needs. In standard regimes, so in the absence of transport barriers or improved confinement regime in tokamaks, I will come back on this later on. So in the standard way of running tokamak plasma, then turbulent develops at ion scales. Then if you want to solve this ion scale in the flux-driven approach, so take into account the back reaction of ion scale on the equilibrium scales, then the mesh grid has to, in 5-dimensional phase space, is of the order of 10 to the 12 grid points. The number of iteration is of the order of 10 to the 6 if you want to cover from the correlation time of turbulence up to the energy confinement time. And you end up with a number of flops, which is of the order of 10 to the 20. And this gives you, if you have for your own petascale tokamak, then you can run a simulation in 1 day. That you would, by doing so, you assume that you have a petascale and that you can run the petascale supercomputer at the nominal performance, which is not the case. Basically, we can run it at most at a few percent of performance, so it's more likely that you will need in the end 100 days. And this is typically the amount of time that we need to run large-scale simulations in present-day tokamaks. But then, if you want to go into the improved confinement regimes, in the case where part of the ion scale turbulence in some regions of the tokamaks has been reduced and even has disappeared, then in this case, what you have to take into account is the turbulence that develops at smaller scale, even smaller scale, which is the electron scale. And in this case, because the electron scale is much smaller spatially and develops on much shorter time scales, then the number of flops increases by 5 orders of magnitudes, and then you end up with 100 days at the exascale level. So you can see that for sure the needs are fairly large. Obviously, there are alternatives which are developed to further reduce the numerical cost. There's a kind of hybrid modeling of fluid, coupling the fluid and kinetic descriptions, multi-scale approach as well, which I described previously. But you can see that there's really a need for supercomputers when worrying about the turbulent transport in tokamak plasma. Let's go to the two last points and detail this two interplay. First, the interplay between the electron and ion scales. So I will report on recent progress which were made in this area. So as I said, when you worry about this interaction between electron and ion scale, then you can freeze, and this is basically what is done in present-day simulation. You can freeze the equilibrium scale. What does it mean? It means, and this is sketched on this diagram here, you prescribe a given equilibrium gradient, which will remain constant in time during the simulation, on top of which you allow the fluctuation to develop. And those fluctuations develop at the ion scale and the electron scale. And what you're then interested in is in the coupling between those two scales, which are small scales with respect to the equilibrium. Conversely, if you're interested in the interplay between the ion scale and the equilibrium scale, then in this case, you have to relax the assumption of constant equilibrium, and this is the flux-driven regime, where the gradients are, the mean gradients are free to evolve under the balance effect of a heating source. So the heating source that you put in the system is reminiscent of what occurs in the tokamak plasma, where you heat the system with waves, RF waves, or a neutral beam. So you have a heating source in the system, and then the gradient react to the source and end up to a saturated regime under the effect of turbulent transport and possibly collision transport as well. So this is an example on the sketch here, where you can see that the source, the radial direction is the x-axis, and for various magnitude of the source located in the core plasma here, you can see that the plasma, the system, develops a pressure profile which is constant in time, which is saturated and fluctuates around mean values. And when you increase the heating source, then obviously the pressure profile builds up and develops larger gradients. So far, we are not able to run flux-driven regimes by coupling the equilibrium, the ion, and the electron scale. So we have to make some assumption, some simplified assumption regarding the electron scale. What is important to notice is that recently a paper, several papers pointed out that it's critical to take into account this interaction between the equilibrium scale and the ion scale for ion scale turbulence, especially close to the threshold. So when turbulence develops close to the linear threshold, which we mentioned previously, or nonlinear threshold, and actually those regimes are the one in which the experiments take place. It appears that the gradients that we measure experimentally are fairly close to the nonlinear threshold. And in this case, the simulation, as exemplified here, show that whether you run the simulation in the flux-driven regime or in the gradient regime, then the heat flux, the prediction in terms of the heat flux can be completely different, and especially in the region where the temperature gradient is close to the threshold, close to 7 or 8 here, you can see that the flux-driven regime can predict an almost vanishing heat flux, turbulent heat flux, while the gradient-driven regime predicts a much larger flux. So those two kinds of approaches are completely different in the prediction they can make, and then they would lead to completely different prediction for the energy confinement time in ITER. So it's extremely important to wonder about the way you perform the simulation, because it has some physics issue behind. So let's detail the interaction between the ion and the electron scale in the gradient-driven regime. There are various instabilities that develop at the electron scale. There are electromagnetic instabilities like at the electron scale. Those are the electron temperature gradient-driven modes. There are some others also, like kinetic ballooning modes, which I do not mention here, but one of those is the so-called the ETG. At the ion scale, we already mentioned the ITG and TEM, which are carried by the certain class of electrons. There's also microtearing modes, which are an electromagnetic instability, which can develop close to the edge. And what is presented here is an analysis of the experimental, based on the experimental profiles. So you take the profile measured experimentally, the temperature profile, the density profile, and then you look whether some instabilities are unstable or not, and if they are unstable, you can compute their growth rate. So this is what has been done here. As a function of the normalized minor radius, as a function of the wave vector of the instability, you plot the growth rate. And for different experimental measurements, for Aztecs machines and for the jet machine. What you can see on Aztecs is when you go to the edge, close to 0.8, 0.7, 0.8, then you develop micro-tearing modes, and you have several other instabilities. You have the ITG and the ETG. And you can see, as I said, that micro-tearing and ITG develop at fairly large scale, so scales which are larger with respect to the ion Larmor radius, and electron scales develop at scales which are ky rho s, ky the colloidal wave vector, rho s is the basically the ion Larmor radius. So ETG develop at scales which are smaller than the ion Larmor radius and up to the electron Larmor radius. If you look at the instability which are linearly expected on jet discharges, then in this case, micro-tearing do not seem to be present, but you can have trapped electron modes at the edge and on top of ETG. So when performing simulation, nonlinear simulation in this region, close to the edge, what the linear analysis tells you is that you have a bunch of instabilities which are potentially present, and non-linearly you would be tempted to treat them on an equal footing. Unfortunately, so far it's not feasible, so you have to split the problem in different pieces, and the first piece is to treat the ion and electron scale at once, and not treating the interaction of the ion scale like ITG, TM with the much larger scale, which are the equilibrium scale. So this kind of analysis has been performed in the past, those are extremely time-consuming simulation, and there were a controversy when performing simulation without this interplay with the ion and the electrons. So there have been a few simulations where only electron scale turbulence was modeled with a simplified assumption for the ion response. And in this case, the people in those two simulations reported a fairly large transport. And some other simulation where the ions were given a kinetic response, not so simplified as the first papers. In this case, then the ETG-driven transport was fairly small and no more than 15% of the total. And actually, we managed to understand this discrepancy between the two kind of simulation by the fact that the second simulation where ions were treated kinetically, so this simulation allowed for the interplay between the ion scale and the electron scale, which was not the case in the first simulation which were performed. And actually this interplay becomes really important close to the ITG threshold, where the ITG becomes small and the magnitude becomes small. So a further simulation were performed recently, and this time with the electron and ion scale treated really at the right mass ratio. And treating the right mass ratio is extremely difficult, because then you will have to account for the true difference of scales between ion and electrons, and the bias scales, the ratio between the two scales is of the order of 60 in this case with the right mass ratio. And in this case you can see the differences on top here on this figure. You can see the structure of the electric potential in a simulation where only the ion scale was resolved. And on the bottom, you can see the same simulation where both the ion and the electron scales were resolved. And in this case, you can see that there are small corrugations of the structures, first of all, and second, that the magnitude of the structures is also a bit reduced by roughly a factor of 2. How to understand this? Well, this can be understood as a result, as I mentioned previously, as a result of the interplay between the ion and the electron scale. First of all, the interplay between the ion and the electron, so the impact of the ion scale on the electron scales. When the ion scale turbulent develops, by nonlinear coupling, turbulent fluctuation develops small scales by what is known as energy cascade towards small scales, and then it can feed the electron scale turbulence. So that's one way, by giving energy to the electron scale. So ion scale cascades toward the electron scale. But what is most important is the fact that the electron scale, which develops at small scales, has a tendency to develop large-scale structures, radially elongated across the magnetic surfaces, and which lead to large transport. But the point is that those large-scale structures are sheared apart, are torn apart by the ion scale, provided you account for this ion scale turbulence. So this explains why. This explains actually this figure. Let me explain this figure here, where you have the colloidal wave number again versus the effective diffusivity, which is a measure of the transport governed by various classes of turbulence. If you perform a simulation with only the electron scale turbulence, which is in green, then you have a large transport. Honestly, if you account for the ion scale turbulence, in this case, the turbulent transport at the electron scale, so large ky rho I, then the magnitude of the diffusivity is much reduced, and this is due to the fact that those large-scale structures of the electron scale turbulence are disappear because of the interplay with the ion scale turbulence. We can also notice, but this is a bit less dramatic, an interplay between the electron scale and the ion scale when you go to larger beta. I will not comment on this issue. Let's come now to the last point, and the interplay between the ion scale and the electron and the equilibrium scale. So, coming back a little bit more on this issue, from the kinetic point of view, this is the Vlasov equation, or the gyrokinetic equation takes a similar form. On the left-hand side, you have the time evolution of the distribution function, f. H is the Hamiltonian. The brackets here are Poisson bracket, so they account for the trajectory of the particle in the phase space, 5-dimensional phase space. And on the right-hand side, you have two terms, the collision operator on the one hand, and the source term. The source, which can be heat source, momentum source, particle source, any kind of sources that you have to account for in a tokamak gas mass. So this equation, with f being the total distribution function, can be split in two different equations, one for the fluctuation and one for the equilibrium distribution function. Those are really equivalent, those two. What is done in the gradient-driven approach usually is that the second equation on the equilibrium distribution function is not accounted for. And this equation actually tells you that the equilibrium distribution function evolves due to the coupling, the nonlinear coupling of the fluctuations, which is actually the divergence of the flux, of the turbulent flux, and the source which prevents the gradients to completely relax. The flux-driven approach solves those two coupled equations at once, and then the drive of the fluctuations evolves because the equilibrium distribution function evolves due to the second equation. And actually what we have shown is that this coupling can lead to a new source, a new way of transporting the heat or the particles, which is an avalanche-like transport. And how to understand this? Imagine at T1 you have a strong gradient that develops at certain region of the system. Then the strong gradient is such that the instability will develop in the region of the strong gradient, here and here. And because the instability develops, then you have turbulence, which will develop, increase, and govern turbulent transport. And what does the turbulent transport? The turbulent transport has the effect of flattening the equilibrium gradient. So you flatten locally the gradient, and since you flatten locally the gradient, then you steepen it on both sides. So you have a steepening of the gradient that propagates downwards and inwards. And this is the essence of the avalanche-like transport of ballistic propagation, which I will come back on in a few minutes. This has been observed in several simulation, flux-driven simulation, where you have here the front that develops and that propagates almost ballistically on large scales. So this is the difference between gradient-driven and flux-driven that we already saw. And this is an example of a simulation, of a gyrokinetic simulation on the right, where you have the heat flux, the turbulent heat flux measured in the simulation as a function of time and as a function of the minor radius here. The heat source is located close to the core, close to point 3. And you can see that the heat flux is made of such structures that are almost aligned. Those are those correspond to avalanches which propagate on radial distances which are much larger than the correlation length of turbulence, which is of a few iron armor radius. The propagation velocity of those avalanches is of the order of rho star times the thermal velocity, so it's fairly small. Rho star is of the order of 10 to the minus 3 in ITER, the thermal velocity of the order of 10 to the 6 meter per second. So this leads to propagation velocity, which can be fairly large in ITER, of the order of a kilometer per second. There have been some effort to understand and to model those this kind of transport by reduced transport models, and some analogy with sand piles was developed. They exhibit intermittency. They exhibit a frequency spectrum which goes like 1 over f, f being the frequency. And so you can find on those references here various papers. The last point I can mention is that there have been a few experimental evidence of this avalanche-like transport. Those are extremely difficult to measure experimentally because of their complex structure in 3 dimensions. The second structure, which developed at mesoscale, so the interplay between the ion scale and the equilibrium scales, are so-called zonal flows. What are zonal flows? Zonal flows are flows which are large scales as compared to turbulence. You have here an example in the Jupiter planet, which is taken from the pole, from one of the poles, and you can see those bands here, and those bands correspond to a structure which are rotating in one direction and in another direction nearby. So there is a shear flow in one direction and in another, and those large-scale flows are actually, as far as we understand the physics, are actually driven by the small-scale turbulence which develops in this atmosphere of the planet. Similarly, in tokamaks, and this comes from the simulation, the small-scale turbulence that develops at the ion scale can develop can trigger the rotation of the plasma on constant on one magnetic surface. So it is large scale because it's constant on magnetic surface. And actually what you will see is that because of this generation by turbulence of zonal flows, each magnetic surface rotates at a different value, at a different velocity. And so you have a shear velocity from one magnetic surface to the other. And this is one example coming from a gyrokinetic simulation performed with the gyrokinetic called Cea, where the color corresponds to the magnitude of the colloidal flow on the magnetic surface. So the axisymmetric axis will be here. This is the low field side, the high field side, and you can see that the one magnetic surface, which is circular shape in this simulation, has one, here for instance in blue, one velocity and another velocity nearby. So it's a shear flow that develops. There are several ways of understanding this, the self-generation by turbulence of these large-scale flows, and one of those comes from modulational instability that couples small-scale fluctuation of the E cross B flow together to drive a large-scale colloidal flow. This is via the R theta component of the Reynolds stress. I cannot go into much detail here, but what I want to point out is some evidence of the impact of zonal flows on the turbulent transport. And here you can see on those two simulations here an example of two simulations with the zonal flows. In simulation, we can arbitrarily remove the zonal flows, which is not not possible, obviously, in experiments. And what you can see is that when you artificially remove the zonal flows, then you end up with structure of turbulence which are much elongating across the magnetic surfaces, so along the right direction. And this kind of simulation without zonal flow leads to a much larger transport. Similarly, if you look at the energy, the turbulent energy carried by small-scale turbulence versus time, this is what you get in the absence of zonal flow. And when you switch on the zonal flows, then part of the energy of the turbulence goes to the zonal flows, and the energy of turbulence is reduced. So it's extremely advantageous to have a regime in which the zonal flows are strong, because then you end up with a small magnitude of turbulent level, and in the end, you can expect a much larger energy confinement time. So zonal flows are beneficial. The point is, what is the way to increase the efficiency of the zonal flow, to increase their level? And this is obviously not easy to perform because it's a non-linear process, as you understood. So this is really the result. Zonal flows are the result of the self-organization of turbulence. An important point to notice is that zonal flows are somewhat peculiar in this picture because they are linearly damped only by collisions. They are really stable linearly, so they require kinetic calculation because all fluid approaches have another overestimated diffusion. The other point that we managed to show regarding those zonal flows, and this comes from recent modeling, we showed that actually avalanches and zonal flows coexist. They are two different features. Avalanches are large-scale transport across the radial direction, along the radial direction, while zonal flows are shear flows at given locations. And what we observed in numerical simulations actually is that those two beasts coexist in the sense that avalanches develop in between regions of strongly sheared zonal flows. And this can be seen on this picture here, where the shear of the zonal flows is presented here in color. So yellow and black correspond to strongly sheared zonal flows. And in between the zonal flows, you can guess that they are avalanches. The resulting transport is the following. In between the zonal flow, the strongly sheared zonal flows, you have avalanches, and then you have strong transport. Since you have strong transport, the pressure gradient or the temperature gradient is fairly small. And this is what you see in the simulation. At the position of the strong shear, then you have kind of micro transport barrier in the sense that you have a steepening of the profile. And this is detailed on this sketch here, where you can see that the zonal flow, the mean flow developed structures in form of, localized structures. Close to those structures, then you have a strong shear, as you can see here, because you have a negative and positive shear. And because of this shear, you have the development of strong gradient. Okay, strong reduction of turbulence, and then an increase of the pressure gradient. So these are called staircases. And what was even more interesting is that those staircases were first predicted theoretically by numerical simulation, and they were indirectly observed experimentally. First of all, by noticing that at the position of those staircases, those sheared flows, you have a reduction of the correlation length of turbulence, and this reduction of correlation of turbulence, quasi-periodic, was measured experimentally by phase sweeping reflectometry, and also by using back Doppler backscattering on jet. Well, actually, the zonal flows are not the only way of generating shear flows. The equilibrium can provide also some sheared rotation, and this is due to the radial force balance, which is present here. So the turbulence is rotating at a certain colloidal velocity, which is mainly governed by the radial electric field. And so shearing this radial electric field, or shearing the colloidal velocity of turbulence, tends to decrease turbulence and then to stabilize turbulence. Zonal flows are one way of generating this sheared radial electric field, but as I said, radial force balance is also another way. And the radial force balance tells you that the radial electric field states like the density gradient, the temperature gradient, and the parallel velocity as well. If you want to, from this radial force balance, to control the shear of the radial electric field, then it reveals costly, because then you have to use fueling, heating, and toroidal momentum injection, and those are not most efficient way of driving the shear of the radial electric field. Again, shearing the radial electric field is beneficial because it will reduce turbulence and then increase the energy confinement time. Here is an example of another example where turbulence is sheared by a prescribed sheared radial electric field. What I wanted to point out now is the fact that there are some experimental evidence that the shear of the radial electric field is efficient in stabilizing turbulence and in triggering transport wires. And we think that this is the essence of the H mode, which is the high confinement mode. This regime has been actually discovered on the machine, on the Tokamak Aztecs at the beginning of the 80s. And when the system, the Tokamak, the plasma, was heated above a certain heating power, then the people observed that it spontaneously bifurcated toward an improved confinement regime, where the energy confinement time almost doubled. And further analysis revealed that actually at this location, close to the separatrix, close to the region where the fill line, the region in between the closed fill lines and the open fill lines. In this region, actually, when you enter the H mode, spontaneously the turbulence decreases a lot, and here you can see the magnitude of the fluctuation versus time. In the normal regime, which is called the low confinement regime, or L mode, the magnitude of the fluctuation is fairly large, and spontaneously the plasma at some point enters the H mode, the high confinement regime, and with a reduced level of turbulence, and this corresponds to a steepening of the pressure gradient, the pressure profile that you can see here. In the L mode regime, a small gradient and a very large gradient in the H mode regime, close to the separatrix here. So clearly, as I said previously, this is related also to a strong shear that develops on the radial electric field. This is the radial electric field in H mode, and in H mode, you can see that it develops a strong well with sheared region. So there's really a big effort in understanding the power threshold for transiting toward bifurcating toward this H mode to understand more precisely the mechanism and the stability of this H mode as well. And actually, this is certainly the new Everest, which is the core edge turbulence interplay. So if you want to model the transition toward the H mode regime, then you have to couple the core modeling of turbulence with the edge modeling. And one of the difficulties is presented on this view graph here, on this graphs, where you can see the profile, the temperature profile as a function of the normalized radius, typical profile in H mode with the core plasma, the edge region, and here you can see the scrape-off layer. Now, if you plot this temperature profile, the same temperature profile, in logarithmic scale here, and with a radius which is this time not normalized to the minor radius, but normalized to the ion Larmor radius. Why doing so? It's because you know that turbulent develop roughly at the ion scale, so you have in mind that basically, if you want to perform a simulation, your grid mesh has to be of the order of a few ion Larmor radius. And what you
1 hour, Yannick?
Yes?
1 hour.
Okay, I'm close to the end, so it should be fine.
Thanks.
What you can see that if you want to solve the core turbulence, then with a few hundred of grid points in the radial direction, it's okay. If you want to go up to the edge, then you have to you need several thousand of points. And if you want to solve the scrape-off layer, then it's of the order of 10 to the 4 grid points. So you can see that already from this need regarding the grid mesh, it's extremely time-consuming to go through the X1. On top of this, the physics is so more complex because of the geometry partly, because of the fact that you have large-scale fluctuations. So it's really challenging going in this direction. Nevertheless, because it's extremely important to make prediction for ITER regarding this region, and as a complementary effort with respect to the effort which is done presently by the fluid community, the fluid modeling of turbulence in tokamaks, we are pushing the gyrokinetic codes toward the edge. This is an example performed in Gisela, which is the code developed at Cea in collaboration with various other laboratories. You can see two kinds of simulation, one with a simplified boundary condition for the edge here, which was the former way of modeling, and now the new modeling that we have recently implemented in the code, where we take into account the interaction of the plasma with a wall, and in this case, this is a toroidal limiter. So there's a really simplified modeling so far of the so-called scrape-off layer, which is this peripheral region here where the field line intercepts the wall. And you can see that there's some differences, noticeable differences, and especially the appearance of those structures of the electric potential close to the separatrix here in dashed line. And actually, this governs the modification of the fluctuation at the edge. And this is what you can see. What is presented here on this graph here on the top left is the relative magnitude of the density fluctuation in percent as a function of the normalized radius for two kinds of simulation. In red correspond to the new simulation with the simplified modeling of the scrape-off layer, and in black or gray correspond to the former simulation. And when you do not take into account the properly or more properly the boundary condition, then you do not manage to recover the experimental observation that the relative density fluctuation are increasing a lot when you move toward the scrape-off layer. So that there is no way to recover the increase of the perturbation here if you do not take into account the scrape-off layer. We have made several attempts by varying the gradients, by varying several other equilibrium parameters, and it did not cure the problem. So definitely the scrape-off layer revealed to be the critical issue, and I do not detail here the physics, but we managed to understand what's going on in this region. Maybe I can show you a movie just to finish. let me, no, not this one. Yeah, here is a movie of a simulation of Gisela with the scrape of layer. And what is interesting, you can see several things. You can see the small scale turbulence which develops. Interestingly enough, you can see also the plasma which is rotating and which is rotating in different directions depending on the flux of phase that you look at. You can also see that the fluctuations are much elongated along the field line. And the last point that you can notice is that there are some fluctuations that develop here close to the separatrix, and which are another type of instability, which was also suspected experimentally 10 or 15 years ago on Torsupra, which are Kelvin-Helmholtz instability, an instability which develops when the system is developing a strong shear in the rotation. So this is the kind of simulation that we are now performing. Let's come to the conclusion. So obviously, to run this kind of simulation, we need to have access to supercomputers, and this gives you an idea of the increase in CPU time that we consume with the Gisela code as a function of the year, and it's a logarithmic scale in millions of CPU hours, and you can see that now we are at a bit above 100 million CPU hours per year. So, as a conclusions, gyrokinetic modeling is necessary in the core plasma modeling because of the almost collisionless nature of this plasma. It is critical for understanding, predicting, and possibly controlling turbulence and transport in fusion plasma, and hence reaching improved performance. We saw that there is definitely an interplay between various scales, the electron and ion scale on the one hand, the ion and equilibrium scale on the other hand, and the latter is especially important close to the threshold, which is the regime in which the experiment operates actually, and this requires a flux-driven approach. There is some effort to push the codes, fluid codes and gyrokinetic codes towards a global approach. It is not yet achievable, but we go in this direction. In flux-driven regime, that you have to wonder about the boundary conditions. They play a critical role. Physically, this is really important to wonder what is the interplay of your system with the exterior. And actually, tokamak plasma are open systems, so they do interact with the exterior. And one way in this direction is to account for edge and scrape of layer in core transport modeling. So this is the direction that we pursue right now in the various European projects. Multi-physics means that you have to account for the interplay between edge and pedestal transport to take into account the neutrals as well. This is done in fluid simulation and fast particles with the alpha particles, for instance. Gyrokinetic, brute force gyrokinetic is one way, although we try to reduce a bit the brute force by having some alternative ways of modeling some part of the small or large scales. And several other strategies are pursued. Right now, there are reduced models, which are always useful to understand the physics at work, and because obviously they are fast, so they are toy or heuristic models or Quasi-linear framework as well. Yes, I can conclude here. Thank you for your attention. I can listen to your questions if you have any.
Okay, thank you very much, Yannick. You have two questions, sorry. So one right at 11:19, and is can you explain what's more about the scaling law?
The scaling law, okay. Let's come back on the slide. Here's it. Yes, the scaling law. Well, basically, you have a large number of experimental measurements in various machines where you can measure the energy confinement time. It is not obvious, but let's assume that you know how to proceed. You have several machines in which you measure the energy confinement time and in which you measure also some other quantities like the temperature, the density, what else? The safety factors, so the magnetic geometry, you know it. And from this, you can extract the value of some dimensionless parameters, which are rho star, beta, and nu star, for instance. But there are several others: the safety factor, the ratio of the major radius of the minor radius, and then you plot all the data, all the energy confinement time that you have in these various machines. So it's a cloud of points. And the idea of a scaling law is to propose a way of reducing the dispersion of this cloud of points. And the best you can do in reducing this cloud of points, in reducing, sorry, the scattering of this cloud of points, provide the scaling law. Okay? So it's a kind of linear regression. You have to minimize the dispersion of the points. And when you get the minimal way, the minimal dispersion, then you call it a scaling law. And this is what is plotted here. The scaling law looks like this. So from the various points that you had, experimental points, if you plot the same energy confinement time, the energy confinement time here, the experimental one, as a function of what you expect from this scaling law, this is the scattering that you get. So the best that you can do is getting 15 or 16% of the order of, let's say, the 15 or 20% dispersion. Is it more clear?
Thank you. So the question was asked by Francis Clinton, and so I don't know if it's more clear for him. Otherwise, he will say it, I think. The second question is, can you explain about flux-driven turbulence?
Flux-driven turbulence. Okay, so I was not here now, apparently. Let's come to let's go on this slide here. Okay, flux-driven turbulence. If you want to let the equilibrium profile, the density profile, the temperature profile evolve freely, what does it mean? It means that you need a source to build the profile. And actually, this is what happens in Tokamak. Focus on the temperature. In Tokamak plasma, there is heating in the core plasma. You have RF heating, ion cyclotron heating, or ECRH, electron cyclotron resonance heating. You can have also neutral beam heating, neutral beam injection. So you heat your plasma in the core. Then the temperature increases, but it does not increase to hell. At some point, because the gradient develops, then you depart from the thermodynamical equilibrium, and the system wants to relax toward the thermodynamical equilibrium. So the departure from thermodynamical equilibrium drives fluxes. Those fluxes turn out to be mainly driven by turbulence in Tokamak plasma. you have also some collisional transport, but mainly by turbulence. And so the profile, the temperature profile builds up because you have a source, and at some point, I mean, meanwhile, it's the steepening of the temperature gets transported because of turbulent transport and collisions. So the effect of transport is to flatten the gradient. This is the always, I mean, this is always the effect of the transport. It has to fulfill the thermodynamical principle. So in the end, you heat the system, the temperature develops, the transport, turbulent transport pops up once your temperature gradient has exceeded the threshold for the instability, and then you have some relaxation, and the temperature profile oscillates around a mean value with the fluctuations corresponding to the turbulent dynamics. This whole picture is well described within the flux-driven approach, because in the flux-driven approach, you account for the source, you account for the turbulent fluctuations, and you account for the back reaction of the turbulence on the mean profile. This is the essence of what is called the flux-driven approach. In the gradient-driven approach, you do not worry about the source. You assume that the source has developed in such a way to build a certain profile, and you start from this profile. You say, I have an equilibrium temperature profile, I keep it frozen, and on top of it, I let fluctuation to develop. If I have fluctuation, from the fluctuation, I can compute a flux, and this is the outcome of the simulation. But in this kind of approach, you do not take into account the back reaction of the turbulent flux on the equilibrium. The equilibrium profile is frozen, is prescribed, and you just have as an outcome the magnitude of the turbulent flux. Okay? I hope it's more clear.
Thank you very much, Yannick. I think that there is no more questions. So I thank you very much for this webinar. I remind the participants that they can find this webinar on our website afterward, and that you can contact Yannick directly if you have any more questions. So thank you very much and have a good day. Bye, Yannick. Thank you.
Bye-bye.
Bye.